So many different types of resistive forces exist in nature. Now, what exactly is a resistive force? Well, a resistive force is simply a force that impedes the movement of objects. So one particular example of a resistive force that we spoke about earlier is friction. Now, whenever an object such as a box is being acted on by a net force, that net force propels the object. It allows the object to move. It creates motion. So, in this example, our net force acts in the positive direction along our x-axis, so our box will move in the same direction as the net force. Now, what happens is the surface of the box interacts with the surface on which the box is on, creating a resistive force known as friction. Now, friction depends on three things. It depends on the type of surface being used, it depends on the mass of the object, and it also depends on our gravitational constant g, our gravitational acceleration. So the formula for this resistive force known as friction is given by the following equation. So the force of friction is equal to the coefficient of friction multiplied by the normal force. So the mass of the object multiplied by g, our gravitational constant. Now notice this particular resistive force does not depend on the shape of the object, it does not depend on the surface area of the object, and it does not depend on the velocity of the object. Now, other examples of resistive forces that do depend on these factors exist. And one particularly important example is known as drag force. So what exactly is a drag force? Well, let's suppose I take that same box and I take the box and I let it go. So my box will travel from point A to some point B below point A. Now, how exactly does our box get from point A to point B? Well, it's traveling because the gravitational, or our Earth, pulls down on the box. And what it has to do is it travels through air. And air is composed of molecules. And these molecules collide with the box. And they create a resistive force. And this force together is known as drag force. So when objects move via fluids, such as liquids or gases, the molecules in that fluid create a resistive force known as drag force. And the drag force points in the opposite direction of motion, just like the force of friction. Now, drag force depends on velocity, unlike friction. And drag force has a relatively complicated relationship with velocity. So, to uncomplicate things, we're going to make the following assumption. So let's assume that the object we're using is pretty small and that the velocity, the speed of that object is also relatively low. Now, if those assumptions are made, we can find the following, we can use the following formula for drag force. Drag force is equal to negative of B times V, where the negative simply means the drag force is in the opposite direction of motion, as in this example and this example, and the B is simply our proportionality constant. It depends on the type of object being used, the surface area, and so on and so forth. Now, the V is simply the velocity of that object. And notice, as the velocity increases, as our object's velocity increases, the drag force also increases. So, let's examine a free-falling object. So let's look at our box once again. So we have the gravitational pull of our Earth that's pulling down on the box that is perpendicular to the ground. And we have the drag force, the force created by the molecules in our fluid that are exerting a force on the box that points in the opposite direction of motion. So, let's sum up all the forces acting on our box and our object along the y-axis. So let's choose downward to be positive because our object is moving downward. So we have the force of gravity, or simply m times g, minus the drag force, which is simply b times v. And that equals, according to the second law of motion, m times a, where m is the mass of the object and a is our acceleration of that object, which points downward in the same direction as the net force. Now, another way of viewing our acceleration is as the rate of change of our velocity with respect to time. So we take the derivative of our velocity with respect to time. That's, by definition, what acceleration is. Now, notice from this formula that as time increases, the velocity of the box increases, but also our acceleration decreases. In other words, as the box travels downward, what happens is its velocity increases, but the drag force also increases. Because the drag force increases and this stays constant. So this stays constant, this begins to increase, so our acceleration begins to decrease. And that means even though our velocity of the object is continually increasing, it's increasing at a smaller and smaller rate. And eventually, what happens is it will reach a certain velocity known as the terminal velocity. And the terminal velocity is simply the highest velocity that the object can attain. So, at this point, the acceleration, the rate of change of velocity is 0. So we set this equal to 0. We bring this term to this side, divide both sides by b, and we get that our terminal velocity of the object is equal to this formula. It depends on mg and our b. So this is known as the terminal velocity, and the graph looks like this. So at the beginning, our velocity is increasing at a high rate because our drag force is very low. But eventually, the drag force will begin to approach the value of mg. And when it equals mg, when these two equal one another, this is 0. And at that point, our object has reached its highest possible velocity.